We have a test on Friday. Today we'll finish up, I think, everything we need to finish up from chapter 4. Yes? Talk about precipitation reactions and redox reactions and stuff like that. Wednesday, hopefully, we'll have the whole day to review questions from your pretest that you've been working on diligently. Wednesday night, you should have those submitted. By what time? 7:59 p.m. Yeah. If they're after that, what's the score? 0. Yeah. Not 5 or 6 or some partial credit, but what? 0. Okay. Computers have no mercy. Right? So make sure that you save and submit before then. Thursday's a science seminar. And then Friday will be our second class test. And then a second reading will be distributed on Friday so that you don't get bored over the weekend, right? And then you have something to hand in on Monday. So, so lots of stuff going on here in life. Busy week ahead of you. Yes? So hopefully you are rested from the weekend, right? Because you need all the strength you need.
Don't want us to get bored?
No, I don't want you to get bored. That'd be terrible. Yes? So, what's our science seminar this week? It's this guy from Stephen F. Austin University, which is down the road here toward Houston. He's going to talk about open source textbooks. This has been one proposed solution to the cost of textbooks, right? Making everything open source, right? Looked at it in chemistry a while back, but they couldn't find anything that was as good as what we have, so we didn't do it. But who knows? Maybe we can now, right? So if you want to explore the idea of open source materials for textbooks, okay, especially in the math and sciences, here's something to come to and see what's available out there, see what the movement is. Yes, because textbooks are expensive. Maybe you can make them all open source, and the only cost is your printing cost if you want to print them. Yes, that would save you money, right? Yes? All right. So coming out for that on Thursday. Yesterday when we were together, and yesterday I mean figuratively the last time we were together, we talked about molarity and concentration. And the solution to all your problems is concentration. Yes? All right. I talked about V1, M1 equal V2, M2 for dilution problems. Talked about solution stoichiometry, starting not with grams, but starting with a volume, going from a volume to moles, moles to moles, and then moles to whatever you want, volume maybe. Yes? And we looked a little bit at the different types of aqueous solutions and examples with solution stoichiometry. So let's look at some more of those here before we go into other things. So remember the difference between a salt and a sugar. So here's your dissociation of a salt. Note that the ions are independently dissolved. You have the cations that are dissolved by a sphere of solvation. And you have an anion dissolved by a sphere of solvating molecules. Looks like a ring, but really it's 3 dimensions, but then you couldn't see the ion inside. They put the whole sphere there, right? Okay, so we no longer have sodium chloride, but what we have is sodium dissolved by water, so we say sodium aqueous, and the chloride ion aqueous. We say that salts break apart when they are dissolved in water. Yes, they're no longer together. They are independently dissolved ions. Right? Oftentimes we just write this, though, as NaCl aqueous. But you should recognize that when you write this, what you really mean is that.
One's the molecular, one's the complete ionic.
Yeah. So know what that means when we write NaCl aqueous. It means that the ions are pulled apart from each other, dissolved by water molecules. Actually, there's 2 or 3 different layers of spheres around them. Yes? And that's what you have. This, in contrast to something that's not ionic, something like a monosaccharide, a sugar unit, okay, of glucose or something, okay, in which the whole molecule is solvated by water here. It doesn't have a charge, and so it stays together as that unit of thing. Yes? All right, so that's a sugar solution. It still dissolves, right? It still goes into solution, still nice and colorless and clear, but there's no ions there. The whole molecule is a neutral thing, and so you don't have the ions. What don't you have?
No ions.
And this makes a difference when you try to pass a current through water. If you have deionized water, right, you aren't going to get a current through it. But if you have salts dissolved in the water, okay, like sodium chloride, we have independent cations and anions floating about, okay, you will have a strong electrolyte. Those charged particles can carry a current, and you can light your light bulb. If you have a sugar unit in there that doesn't have any charge, there's nothing to carry the charge, yes, and you've got no light bulb. If you have something like a weak acid, which sometimes is pulled apart and sometimes not, you'll get, a little bit less current. Yes, Ken?
Would you just have to memorize which ones are weak and which ones are strong?
If they're not strong, they're probably weak. So it's a lot less strong ones than there are weak ones. So if you know the strong ones,
You should be fine.
you should be good. All right, now, not every salt dissolves, right? So we have these little rules of solubility. Okay, that works pretty well. So there's ways to read this thing. So let's take, for example, sodium chloride. We know sodium chloride dissolves, yes? And if we look at this little list, we see here the sodium cation on this list. And it says compounds containing the following ions are generally soluble. Generally means most of the time. And if it's most of the time, that means there might be what?
There might
Exception.
be exceptions.
But is there any exception with sodium?
Nope.
No. So any salt that you make in which sodium is the cation will be soluble. Sodium chloride, sodium fluoride, sodium bromide. Yes? Right? Okay. All be soluble. Same thing with things like lithium and ammonium. There are no exceptions. So these guys are good to know. Here are some more no exceptions. This first two set. All nitrates are soluble. Sodium nitrate, potassium nitrate will all be soluble in water. Yes? There you go. All right. Now look here. Some of these things aren't soluble. Here are some anions. And when these anions are paired up with these cations, they won't be soluble. So if you had silver chloride, would that be soluble? No, because one of the exceptions. Mercury, okay, so you got Hg2, that's a 2 plus, so how many chlorines do you need? 2. Would that be soluble? No, because it's one of the exceptions to the rule that most chlorides are soluble. All the chlorides are soluble except these things that have silver or lead or mercury. Those things will not be soluble. We call them precipitates. They will fall out of the solution. Yes? Most sulfates are soluble, unless the sulfate is with what?
Strontium 2 plus, barium 2 plus, lead
Ooh,
2 plus.
look at that. These guys
Ag2
again.
2 plus.
Lead and silver show up
Copper 2
again.
Or calcium 2 plus.
Yep. All right. Oops. Now, there's another set of rules down here. These are compounds that are generally what? Insoluble. What does it mean to be insoluble? Not soluble. Yeah. So most of your hydroxides are not soluble. But we know that one of our favorite bases is what? Sodium hydroxide. Yes? And, we say it's in solution. Well, there's an exception with who? Sodium. Because what do you know about all sodiums?
All sodiums are soluble.
Without exception. Okay? So if hydroxides generally aren't soluble, but they're paired up with sodium, and all sodiums are soluble, well, then the sodium hydroxide must be what? Soluble. Yeah. So you see how to play the game here? Yes? Okay. So all calcium, or all carbonates, are mostly insoluble, unless you're with one of these cations. Right? Mm-hmm. Yes?
Back on the ones that are soluble,
Mm-hmm.
the third row,
Hmm?
Why would that be Hg2Cl2? Why would it not just be Hg2Cl?
Because mercury always goes around as a diatomic cation. It's a funny guy.
Does that have anything to do with the fact that its state, or its normal state, is in liquid form?
No, well, it might, but mostly has to do with the fact that it's way down there in the periodic table and funny things are happening to it. Yes. We'll have to talk about that some other time. It's a good thing to notice that. All right, now, if you know the solubility rules, you can predict if a reaction is going to occur between ions such that they will precipitate out. Yes?
Yes.
So let's look at what we call precipitation reactions. So here we go. We got potassium iodide. This is aqueous, which means what? It's dissolved. We really have K plus floating about and what? I minus floating about as independent ions dissolved by water. We also have what floating about? Lead, 2 plus, yes? And who else? Nitrate minus. All these guys are floating about. Here's pictures of them. Yes? You can see the potassium there floating about by itself, the lead floating about by itself. Right? Yes? Those are pictures. Now you ask yourself, okay, so here's the story. You know, potassium and iodide come to the dance together. Yes? Right? They get in the water. So, water polo dance. Yes? And they separate. Right? They came together, but then they went their separate ways. Same thing with lead and nitrate. Right? Well, look at that. Lead gets to come with 2 girls. What a guy. I mean, that's just not fair. Right, guys? I mean, given the ratio here, I mean, all right.
Well, he gets payback.
All right. So, lead comes with 2 girls, 2 nitrates. Yes? Maybe they're twins or something. I don't know. Bad deal there. All right. So, now the question is, which of these ions can get together here and form a precipitate? Well, let's see. Let's check out potassiums. What do we know about potassiums? Yeah, so does it matter if potassium is with the iodide or potassium is with the nitrate?
Nope.
Nope. Potassium is always going to just hang out by himself at the dance, stand against the wall, and hope, you know, some girl might ask him or something. Right? Yes? Mm-hmm. And it never happens. Okay.
Poor fella.
Right, because, you know, he's staring at his shoes when the girl comes to ask and he isn't here. Right? Mm-hmm. Right, guys? All right. Okay, so let's check somebody else then. What about lead? Can lead form any compounds with anybody?
Yep.
Okay, lead has some exceptions here and an exception there. With what ions?
Chlorine, bromine, iodine, and
Yeah.
sulfate.
And who do we see here? Iodide. So we can take lead and iodide together. Now it's lead 2 plus, right?
Yes, sir.
And it's iodide minus, so that means lead gets how many girls? 2. Yes? Lucky guy again. Right? Mm-hmm. There we go. So, there he goes. And now this is not going to be dissolved. This is going to be a solid. There it is, written as lead iodide solid. What do we have here? It says potassium nitrate aqueous. But we know we really have what? K plus floating about and nitrates floating about. Okay? So this is what we have before the reaction. We have a reaction. It forms this as a solid. And then these guys are still there floating about again. So what's floating about before and after?
Potassium and nitrates.
Yeah, the potassiums are floating about before and the nitrates are floating about before. Yes? So they're the same thing on both sides of our reaction arrow. Right? If you subtracted them off from both sides, they just disappear. Yes? We call those spectator ions because they're like you guys sitting in the bleachers. And all the athletes are working hard. You're not doing anything. You're a spectator.
They're just
You don't really count. Right? But what counts is the guys participating here, the lead and the iodide. So we say that we have lead, 2 plus, aqueous, plus, how many iodides do we need? 2. Iodide minus aqueuses, right? React to form lead iodide. And we call that equation then the net ionic equation. Because it doesn't include those spectators. It only includes the net That's what's going on. All right? Yes?
I have a question.
Yeah.
How do you know that it becomes a solid?
Because the rules say that it's going to precipitate. How the rules say it? You look and you say, well, what do we see about iodide? It will form a soluble solution unless it's with who? Lead. Yep. So you got to know the rules and how to use the rules. Yep. So there we go. So here's another example. Potassium iodide plus sodium chloride, right? Mix those two together, and then you see what happens. And what happens? Nothing. I mean, you can write potassium chloride, but it's kind of silly. You can write sodium iodide, but it's kind of silly, because what do we know? We got K plus here, I minus, sodium plus, right? Plus chloride minus. And what do we have on the other side? K plus, CO minus, sodium plus, and I minus. Yes? They're really all just ion floating about in the solution. Yes? You could write Ki aqueous or KCl aqueous, but it doesn't change what's going on in reality. In reality, they're all just ions, because none of these, if you look at the rules, are going to precipitate. All the potassium ions, any exception? None. Sodium ions, any exception? None. So you got two guys coming to the dance who never, ever have a dance. Doesn't matter who the girls are. These guys, I mean, they're medals on the left. They're, losers. Yes, big time losers, right? So, sad story there. But that's it. So, all ions are still present as ions. There's no reaction. Nothing happens. Yes, even though you could write it like something happens, right? Still, nothing happens. It's all in their head. They're just dreaming about it. Yes? Mm-hmm. Okay. So let's talk some more about ionic equations here. We have the molecular equation. Here it is. KOH written aqueous, right? We really know that KOH is really separate ions, right? And then you make the ionic things over here. Yes? And there's the solid thing. So we call this way of writing the equation the molecular equation. And you guys saw this in your homework, right? This. Now if you want to make the ionic equation, we write everything in its ionic form, right? Which is really more close to what reality is. Yes?
For the test, are we going to be given that chart that you put
Boy,
up?
don't you wish.
Yeah.
Yeah, you better hope and pray. Yes. Mm-hmm. But I wouldn't count on it, right? Ah. It depends how nice I feel, And when people ask me for things, I'm less nice, right? So if you just study hard and plan on knowing them, maybe I'll be nice. Yes? Mm-hmm. Okay. I like donuts, All right. Okay. Then there is what we call the net ionic equation, right? And what's the net ionic equation?
The net ionic equation is an ionic equation with no spectator ions.
Yeah. Who are the spectators here? The things that are there before and after, right? Who else is there? Nitrates before and after. So we don't use those guys, knock them out, and you see what's left, right? We knock out who is it? The potassiums and the nitrates. Okay, what do you have left? OH and magnesium, and then the solid that they form. Okay, all right, are you guys with me on molecular, total ionic, or complete ionic, and net ionic equations? Yes?
So net ionic is basically just removing whatever stays.
Yeah, whatever you see on both sides, it's like +3 on both sides. Well, just take away 3. Yes, you don't need it, right? Okay, this is what's really happening. All right, so fun stuff there, yes? So again, the net ionic equation excludes the spectator ions. Are you guys spectator ions? What are they going to say about you at the end?
Adios.
Yeah? What's the net Maria life? Yes? Mm-hmm. If you're going to include, are you going to be included in the reaction? Now, acid-base reactions are just precipitation reactions, but they're simpler. How's that? Okay, well, let's take a look here. Here's your acid, right? What do we know about acids? Here's your one of your favorite ones, HCl aqueous, we say. But what does that really mean? Yeah, you got a hydrogen ion and a chloride. This thing breaks apart. And actually, even this is kind of a bad thing to say, because really the H plus reacts with water and makes this thing called a hydronium ion. But we're going to pretend it doesn't for right now. Yes? So your HF or your HCl breaks apart. Yes? And it makes ions. Now, this acid we say is a strong acid because it does this one way. Note the one-way arrow. Yes? And it completely ionizes. Whereas HF, we say, is a weak acid. And note you have this two-way arrow here, which means it goes back and forth. Yes? And you might think, oh, weak acid, it's not as dangerous. But don't let that fool you, right? Because HF goes right down to your bone, burns right through your flesh, eats through glass. I think that's a little bit dangerous. Yes? Even though we call it a weak acid because it may dissociate but then come back together. Okay? All right. Now, what about an acid plus a base? Well, we call these neutralization reactions. Okay? Here's an example. So you got nitric acid, and you guys know how to name all your acids, right? Yes? Okay? And here is calcium hydroxide. That's your base. Yes, calcium's always +2, so calcium hydroxide's easy. Now you ask yourself, what's the products? Well, what do we know? All nitrates are what? Soluble. Yes. What do we know about the hydroxides? They're mostly soluble, with a couple exceptions. Yes? Any exceptions here? Nope. Nope. Well, the only guy you got there is calcium, or who's the other guy you could hydroxide could join up with? H. So remember, you're coming with the cation and the anion. In this case, the cation is the H plus. Yes. Here you got the cation and the anion. Calcium isn't going to join a precipitate with nitrate. Nope. But can H and OH react? What would it make? It'd make water. And then you'd have the calcium nitrate as a dissolved salt. Yes? And you'd need 2 nitrates for every 1 calcium because the calcium is +2. Yes? Right. So in an acid-base reaction, we always form a salt. Most of the time, just about all the time for you guys, that salt is going to be soluble. Right? Yes? And the other thing you make is what? Water. Yeah. So soluble salt and water is what you form in what we call an acid-base neutralization reaction. So it's just like a precipitation reaction, except you know what the answers are. What's the answer?
Salt and water.
Yeah, salt and water. And it's about always that salt is going to be soluble. The only thing that's new that you're making is the water. Yes? So your net ionic equation is what then? H plus OH minus goes to what?
H2O.
H2O. Because these other guys, the nitrates and the calcium, they're going to float around before and they're going to float around after. Yes, they're just going to be spectators. So this is your net ionic equation. Yes, whenever you see an acid-base reaction, okay, unless the salt formed is insoluble, this is going to be your net ionic equation. Pretty easy. Yes? What's the net ionic equation for an acid plus a base in aqueous systems? H plus OH minus goes to water. Yes? Okay. So fun stuff there. Yes? And here it is in pretty print. There's your net ionic equation. H2O liquid. There it is. All right. Good stuff there, yes? So here's some common acids. A lot of these you already know because we went through them when we named them. Right? Yes? And here's I think this table's in your book too someplace. Perchloric acid, explosives, woohoo, cool stuff. Nitric acid, sulfuric acid, hydrochloric acid, phosphoric acid, chloric acid versus perchloric acid. You guys know the difference. Acetic acid, HF, hydrofluoric acid, one of your binary acids there. carbonic acid in your soda pop. Here's hypochlorous acid. Remember that one? That was fun. Here's boric acid. Okay? Use that to kill cockroaches and stuff like that. Okay? Nuclear reactors use it. Okay? Put in eye washes too. Okay. All kinds of stuff there. Here's some common bases. Yes? Sodium hydroxide, probably one of your favorite ones. Potassium hydroxide, calcium hydroxide, magnesium hydroxide, ammonium hydroxide. Just about all these are what? Hydroxides. But it doesn't mean that all bases are hydroxides. Here you've got a base, sodium bicarbonate. Any hydroxide in that? No. Okay? So it depends how you define your base. Which ones are a base? Okay? Right? You probably define bases in high school as things that have hydroxides in them, but it doesn't always have to be the case. Okay? So these are some common bases that you've probably been using in your homework already. And again, if these bases are not strong, then they are probably what? Weak. So if you make a list of the strong ones, and it's not on your list of the strong ones, whether it's a strong acid or a strong base, okay, then it's probably what, Maria? Manual, it's probably what? Weak. All right. Let's see, boy, you failed that one. Shucks, I know that was a freebie. All right. So here you go. Here's a story of the World War I pilot neutralizing one of the enemy's strongest bases there by adding HCl to the sodium hydroxide. All right, enough of that silly nonsense. All right, let's do some problems here. Yes? Write the molecular ionic and net ionic equation for the reaction of aqueous nitric acid with aqueous calcium hydroxide. So you need to know, what is nitric acid?
Nitric acid, that would be the nitrate ion.
Yep.
So NO3, that has a charge of -1, so HNO3 aqueous.
Yep, and then you got calcium hydroxide, and you know you need to have two of them, two hydroxides, because calcium is 2+. Now you know that these guys are really divided into their ions, and you ask yourself, well, what can they form? Well, they're going to form a salt, the calcium nitrate. Yes? And is that calcium nitrate going to be soluble or insoluble? Soluble. What do we know? All nitrates are soluble. No question about this one. Don't even have to look it up because you remember that rule. And what's the other thing that we form? Water. Yes. All right, so that's our molecular equation. Yes?
It's not balanced.
Not balanced?
No, sir.
Oh, we need two of these guys. Okay. And then we'll need what? Two of these guys. Yes? All right. So there we go. All right, now, that's our molecular equation. Balanced. Okay. What would be the ionic equation? Yeah, you break the HNO3 up into H plus and an O3. Break the calcium hydroxide up into calcium plus and OH minuses. Right? Yes? And what's going to be the net ionic equation?
H plus OH is equal to H2O.
Yep. That's what it always is, unless you have an insoluble salt. And this one is not an insoluble salt, it's soluble. Okay? So let's look at this in pretty print. Yes, because you like that better. Oh, I don't have it in pretty print. Look at that. Huh. Well, I guess you had to have it there. Did you guys get it? Sorry. That was mean of me. Okay. I guess I don't have it in pretty print. That's too bad. Okay. Hope you guys got it. Yes? Let's look onto this thing. Titration. So here is a little adaptation of V1M1 equals V2M2. Okay? Now in a titration reaction, we're adding an acid and a base together. 1 becomes the acid, and 2 becomes the base. And at neutralization, the moles of the acid will equal to what? The moles of the base, if you're going to neutralize these things. Yes? And volume times molarity equals what? Moles. Okay? So moles of acid here, moles of A equals what?
Moles of B.
Moles of B. Okay? And so what we do here, in this particular reaction, we got an acid in the bottom, and we got a base in the top. Okay? Just some generic one, so we got H plus and OH minus. So we are going to add some OH to this, and what's going to happen? Well, the H plus will react with the OH minus, be neutralized to form what? H2O. Okay, so some of the H plus is knocked out as one OH comes in. Here you got two of them that came in. So two of the H pluses got knocked out. How many are left? 3 H pluses still left. Yes? So we had, 3 more OH minuses. Now all 5 of the H pluses got neutralized by reacting with the OH minuses, and everything is turned into what? Water. Yes? So we say that's the equivalence point. That's going to happen when the moles of base that you add is equal to the moles of the acid that you had in your flask. Yes? So, if I know the molarity here, yes, but I don't know the molarity of my original acid, I could calculate it, right? The volume of the base times the molarity of the base is going to equal what?
The volume of the acid times the amount.
Yeah,
molarity of the
yeah.
acid.
And if we know the volume of the acid, we could then calculate the molarity of the acid. Or anything else, right? As long as you know 3 out of 4, yes, you can calculate the missing one. Yes? All right? So, it's just like V1M1 equals V2M2, but it's even simpler because it's just H plus and OH minus. That's the net ionic equation. It's always the same. Yes? So we call this titration. We say the titrant is in the burette, and it's not a hair thing, it's a glass thing. Okay, and we add it drop-wise to our thing that we are titrating until we reach the equivalence point, and we can determine that equivalence point either with a pH meter or by some color indicator when we get to the equivalence point. All right? So at this point, at the equivalence point, okay, indicator might change color, and so we have the same moles of acid as base, okay? And we can figure what the missing one was. All right, so that brings us to the end of those topics from yesterday. Okay, we got time for a quiz, and then we'll talk about redox reactions. Woo! Man, cruising already. Oh, Mondays are so good, aren't they? Mm-hmm. Yeah.
We've still got a lot to learn about oxidation states, and we've only got 20 minutes.
You can do it. Okay, so here are the solutions to your quiz. Remember, V1M1 equals V2M2. Okay, you have 1 liter at 10 molar, and you want to get something that's 2 molar. You go from 10 to 2, that's a change of what? 5, right? So that means the volume has to increase by what? 5. So you go from 1 to 5. Or you punch it all in your calculator and you solve for what you don't know. In this case, what you don't know is the what? The V2. Yes? Solve for that, and you'll find out that it's 5. Okay. The second one, you got this nice precipitation reaction, right? And it says what volume of lithium sulfide is required to completely react with 100 mils of the other stuff. Yes? And you note that in the stoichiometry it's a 1-to-1 reaction there. Yes? But note that here you have a 0.2 molar solution, and here you have a what? 0.1 molar solution. Which one's more concentrated? The 0.2. How much more concentrated? Twice as more concentrated. And if they react 1-to-1 on a mole level, that means if this guy's twice the concentration, you only need what of it? Half as much as the first one. So if you started with, what do we start with? Okay, 100 mils of the first one, then you only need how many mils of the more concentrated one? Half as much, if they're reacting 1-to-1. And here they are. Yes? If you're not sure, you can do all the math. Punch it in there. Milliliter will cancel milliliter. This will give us moles of the cobalt nitrate. We change moles of cobalt nitrate to lithium sulfide. 1-to-1 ratio there. Yes? And then we take, what do we do here? Oh, the molarity of it, 0.2 over 1,000 milliliters, or 1 liter. Yes? And what do you see? The thousands cancel each other. This is 1. So you got 0.1 over 0.2. That's 1/2. 100 milliliters times a half is 50. Yes?
Where'd you get the 1,000 milliliters?
Because it's per liter, per 1 liter, 0.2 moles per 1 liter. I just changed it to milliliters because I started with milliliters. Yes? Yeah, that was convenient for me. Yes, I like to do what's convenient. Yes? Okay. All right, can we do these?
Yes.
All right, not a problem then, huh? If you're having problems with them, come and see me. Okay, see the SI. One topic for today, the redox reaction. And
Here we go.
redox reactions, or what we describe as redox reactions, are really just a system that we make up to keep track of electrons in some way. They don't necessarily represent reality, but they're handy tools to keep track of things. When I go to lunch on Thursday after science seminar, the dean gives me this school card, and I pay for lunch with the school card. Yes? It's got $1 million on it. Yeah, it does. Got $1 million on the school card when I run it to the cafeteria there. So I could buy you guys all lunch all year long. Yes? Mm-hmm. Of course, I'm making trouble with the dean. But is that real? No, it's not. It's all funny money, you might say. But it keeps account of how many times we buy meals and stuff like this. Yes? So same thing here with redox systems. It's not real in the sense the electrons are going from here and there and all that kind of stuff. But it does help us to keep account of things. All right? All right, so let's talk about oxidation reductions in general. You've seen oxidation reactions like this involving oxygen. And we talked about them in organic chemistry. We said when you make more oxygen bonds, that's an oxidation reaction. Yes?
Isn't it real?
Well, we'll talk about that in a minute. Okay? All right, as life goes on, you'll see. All right? So, we have nice independent elements on the left, and then we have a combination of the elements on the right. And the hydrogen you see has now a bond to what? Oxygen. So when we talked about oxidation and reduction in the organic chapter, that's what we said. You make a bond to oxygen, you oxidize things. So we say we oxidize the hydrogen here because now it has a bond with oxygen. Well, we want to quantify this a little bit more than just that sort of idea. Here you have sodium reacting with chlorine, and we also call this an oxidation reaction, even though there's no oxygen involved here. Okay? And so our discussion here of what oxidation and reduction is doesn't have to include oxygen. Okay? Certainly it does include oxygen, but it doesn't have to. Basically what we're saying here when we say oxidation and reduction is we say that the thing that loses electrons is oxidized. The thing that gains electrons is reduced. Then you'll see why in a little bit. Okay? So here the metal, the sodium, is oxidized, and the chlorine gas is reduced. Okay? The thing that reduced caused the other thing to be oxidized. So we say that the thing that is reduced is the oxidizing agent. It caused something to be oxidized. The thing that was oxidized caused the other thing to be what? Reduced. So the thing that was oxidized, here the sodium, is the reducing agent. Okay? So just like if I gave you all my money, I would make you rich. Well, I really wouldn't because I don't have that much money. But if I could, if I gave you the Dean's card, I could make you rich. Yes, because it's got $1 million on it. Right? Yes, the Dean's School card. Remember? Yes. If I gave that to you, you'd be $1 million richer. Right? I would make you rich. I'd be a rich-making agent. Yes? But myself, I would be what? Poor. I've lost $1 million. Man, I could have bought a new house with that card and everything else. Right? But no, not really. I don't think it would work out there. So, that's what we're going to do here. Okay? All right. So, we want to keep track of electrons here. When you have these charged things, it's pretty easy to keep track of these things. And we say that sodium loses, sodium's oxidized, and chlorine was reduced. Now, if we want to quantify this with nice numbers, okay, like 1, 2, 3, we need to assign what we call oxidation states to the elements in the compounds or by themselves. And then we look at the oxidation state before the reaction and the oxidation states after the reaction. Okay? So we need some rules to help us assign what we call the oxidation state of the elements and the atoms in the compound. These are the rules. Okay? A, B through H. So take a minute now, read through these rules, and see if you can assign what we call the oxidation number or the oxidation state to these guys down here. Okay? Give you a minute to try that on your own, and then we'll come together on that. Okay? Musical interlude is in there, yeah. Very soothing while we're working this out. All right, see if you can do this. Follow the rules. Just like nomenclature. Easy when you know the rules, right? Yep. All right, let's come together here and look at these things. Number 1. Oops, sorry. I'm sorry. But we'll be okay. Chromium. Which rule would apply to chromium here? Yep. The oxidation state of a free atom or element is 0. So that guy's a 0. Chromium 3+. The oxidation state of a what? Monatomic ion is equal to its... What's the oxidation state for this guy? Yep, 3+ or +3, whichever you want to say. All right. Now, number 3. Woohoo! You got carbon and you've got the what?
Chlorine.
Yeah, chlorine is a halogen. The halogens usually have an oxidation state of what? -1. So that's 4 -1s. Yes? So that equals what? A minus 4. The whole thing is neutral, so that means the carbon must be what? Plus 4. So it's kind of like you've got an ionic compound even though you know you don't. Yes? Because carbon tetrachloride is a molecular compound with covalent bonds. Yes? It's not ionic. Pardon? It's plus 4. Okay? But we assign the chlorine a minus 1. That's in here someplace. Halogens are usually minus 1. Carbon can vary a lot. Yes? In this case, the carbon is a plus 4. So you're kind of pretending it's ionic when you know it's not. So the oxidation state, we say, is plus 4. Should confuse that with the number of electrons that it may have lost or its charge. They're not the same. The oxidation state is not the same as the charge in a molecular compound. It is the same as the charge in a ionic compound. Okay? All right, let's look at this one. Strontium bromide. Bromide is going to be what?
2 minus.
Minus 1, but there's 2 of them, so you get 2 minus. So the strontium is going to be what? 2 plus. Yes? So this is an ionic compound. That's pretty easy. You just follow what it would be if it's ionic. Molecular compound here, again, SO3. Oxygens are usually what does the rule say?
2 minus.
2 minus. You got 3 2 minuses, right? 3 times 2 minus equals what?
It says sometimes minus 1 though.
Sometimes minus 1. Assume it's minus 2 unless it doesn't work. Yes? Yep. If it doesn't work, then you can make it minus 1. Well, you'll find out. Okay? All right. So 6 minus for all the oxygens. So the sulfur must be what? 6 plus. Yeah, sulfur can be 6 plus. It can lose all 6 electrons, pretending it's an ion. And we say the sulfur has an oxidation state there of 6 plus. Not a charged ionic state of 6 plus, but an oxidation state, which means nothing, right? But what we mean for it to mean. Yes? Which in this case is 6 plus. NO2 minus. Okay, there we go. NO2, let's put it up here. NO2 minus. The oxygen is what? Minus 2. There's 2 of them, so that's a total of a minus 4. The whole thing has to add up to a what? Minus 1, so that means the nitrogen must be a
Plus 3.
plus 3. So that's the oxidation state. It's not the charge on the nitrogen, because this is not an ionic compound. It's a polyatomic anion. Yes? But the N to O bond is a covalent bond. It's not a pure covalent bond, but it's still a covalent bond. 3 for nitrogen. Yes? Each oxygen is minus 2. All right. So let's see if you can do this one in the next 30 seconds. Right? Bromine. What is it, class? 0. Potassium, plus 1. Okay. How about the lithium in LiF?
Plus 1.
And the fluoride would be?
Minus 1.
Minus 1. CO2, what would be the oxygen?
Minus 2.
Minus 2. Therefore, the carbon must be?
Plus 4.
Plus 4. Okay. Oxygen, just about always minus 2, right?
Yep.
Okay. So you got 4 minus 2s, that's what? Minus 8. The whole thing has to add up to a minus 2, so the sulfur must be?
Plus 6.
Plus 6. Okay. Here you got a nice ionic compound. Oxygen is what?
Minus 1.
Minus. Ooh. Well, let's start with minus 2 and see what happens. Okay.
Ain't gonna work.
Yeah, if it was minus 2, you'd have a total of that times 2, which equals to a minus 4. So sodium plus, each one of those would have to be what?
Plus 2.
Plus 2. And where is sodium?
It's on the
Sodium.
first
One.
group.
Could it lose 2 electrons? No,
Yeah.
it can only lose 1. So that doesn't seem to be very good. So let's change this minus 2 to what? Minus 1. Then we can have 2 of them. We'll get a minus 2. And each of the sodiums can still be plus 1, which is this group number. So unless it doesn't work, oxygen is what? Minus 2. What's it take to be a chemist, class?
Hard work, sir. Hard work. And I'm guessing we'll have.
Mm-hmm.
Sorry.